Start.
It is like 10 hours of memory, so it shouldn't matter. You can delete. So it's the same book that I told you about, that book in comprehensive.
Yeah, I got it. I have one now. I like it.
So the same, so the first chapter was special relativity. So I will just go through all those quickly, whatever you know and all.
Okay. Yeah.
So the first thing that was written was the most incomprehensible thing about the world is that it's all comprehensible. That was a good statement. And then first basic thing was vector field. I think you know all this, right? V, X, Y, Z. That's just the vector field V of X, Y, Z.
Yeah.
And gradient is d by dx. I guess you know this, right? D by
Yeah.
gradient and all.
But that's okay.
Yeah. d by dz. And divergence is dvx by dy. Sorry, dvx plus dvy by dy plus dvz by dz. So if v is the gradient of a scalar field phi, then if v equal to delta phi, so phi is the scalar field, and if v is the gradient, then divergence is like phi, which is called the Laplace operator. I guess you know that.
Yes.
Del square. So this is just the basic stuff. And in Euclidean geometry, the internal angles of the triangle is 180 degrees. I guess you know. In Euclidean geometry, two straight lines initially parallel will remain parallel when extended. And the area of circle is pi r square, and Pythagoras theorem is a square plus b square is c square. And the Euclidean metric, as well I think you know, is dl square is dx square plus dy square plus dz square. So the metric g I j will be 1 0 0 0 1 0 0 0 1. And if you convert it to polar coordinates, the metric will be 1 0 0 0 r squared 0 0 0 r squared sine squared theta. I guess you know that as well.
Okay. Sure.
You know that. You know
Spherical coordinates.
spherical
Yes.
polar coordinates. So, and the Einstein summation convention is a alpha b alpha equal to b0 plus a1 b1, like whatever alpha,
Right.
0 to n. So, and the Kronecker delta dij equal to 1 if I equal to j, and if I not equal to j, then it's 0. I guess you know this. Just repeating for sake of completeness. Then the second chapter is Newton in mechanics. And the first law, I will just state for completeness, the object will remain in straight line or uniform motion unless acted by external force. Second is, if net force acts on the object, it will cause an acceleration, F equal to ma. Third is action reaction. Gravitation is gmm by r square. Acceleration is gm by r square, so it doesn't depend on mass, which is
Right.
minus gm by r square in direction of r. So this is different than electromagnetics and all, which
Right.
is one of the reason the principle of equivalence works actually is because of this, because the acceleration doesn't depend on the mass, so all objects fall in the same, like, it doesn't depend on its mass. So
Right.
then divergence of gravitational field. Right. So first of all, gravitational field is given by G, gravitational field at any point r is minus Gm by r square in direction of r. So this is the gravitational field, which is same as acceleration, but the gravitational field at any point r in space is defined as the gravitational force felt by a unit mass placed at that point. And the divergence of gravitation field is minus 4 pi g rho, where rho is the mass density at that point. This is mass density. And tidal forces are due to variation in the gravitational field with respect to r. So because of that, there are those tidal forces, because if there is a lift, even in equivalence principle, like the gravitational field at this end point will be different. So you can figure out, but in a small lift, you can assume that it's very small and you cannot detect it. Then the gravitational potential energy is minus G m1 m2 by r. Then there's a gravitational potential field, which is phi is minus Gm by r. All those things. Then Poisson's equation. This is basically Poisson's equation. This thing.
Now we have the minus energy because we're taking the zero at infinity.
Yeah.
Is-
But gravitational energy is generally negative.
Right, okay.
I don't think it's a convention, but
Yeah.
it's
okay.
actually negative.
I was surprised when I first saw that, because usually I think of it as being, I guess sometimes you take it, I guess for purposes of cosmology and stuff, you're always taking it at infinity.
Yeah, I think at infinity is zero. How much work you do from bringing it to from
Yeah.
infinity to. But there's okay, yeah, that is negative. I don't think it's a convention. I think it's really, maybe it's a convention. No, I don't think it's convention.
I think it's a convention,
Mm.
because a lot of times when you're just looking at an object, when you're doing other kinds of problems, you think of the energy as, well, I think with energy you can always set zero wherever you want it, but except sometimes you might run into trouble.
But I think the thing is, if you are on Earth, in order to take you to infinity, you will need this much energy. You need to spend this much energy, actual
Yeah.
energy. So
Yeah.
you can say that when you come in gravitational field, you lose this much energy, because if you want to get out, you will have to spend this much Gm by r
Yeah,
to go there.
Yeah.
So in that sense, it's really
Yeah.
negative.
it makes sense.
So Poisson's equation can also be written as del square phi equal to minus 4 pi g rho, where phi is this gravitational potential field. Then gravitational acceleration, no, sorry. So for this, if the point is outside of mass, like if there is Earth and if you consider a point here, then this will be zero.
Yeah.
Then the other thing is, important thing I think, is inertial frames. Like it's a frame where which describes, I got it from Wikipedia, it's not in this book, but that describes time and space homogeneously isotropically in a time independent manner. And all inertial frames of reference are in a state of constant rectilinear motion with respect to one another. It has to be rectilinear, I think. It's circular also, is acceleration.
Yeah.
Then principle of least action, and the other thing is non-inertial frames. So non-inertial frames is basically frames which have acceleration. So the laws of motion do not take the simple form they do. They take in inertial frames, and laws vary from frame to frame depending on the acceleration. You have to have to explain the motion of bodies entirely within the viewpoint of non-inertial frames, fictitious force must be introduced. And I think it relates to the centrifugal force and Mach's principle that you were talking about.
Yes, it does. It does.
So also looked upon Mach's principle. It says that a very basic definition is local physical laws are determined by large-scale structure of the universe.
Yeah, I think Mach's idea was that all motion should be relative.
Yeah.
So even accelerated motions were going to be relative to the preponderance of mass.
Yeah. So the last, his idea was like large-scale structure of the universe. It defines physical laws. Like one example they gave was if you are standing still, like the stars are at rest, and your hands are down, and if you like start rotating, your hands automatically go up and stars are spinning. So he's saying that they are related, but it's very vague. They are saying.
Yeah. So this is Mach's idea, but this isn't an accepted.
Yeah.
This is a controversy.
Yeah, from what I heard, even general relativity doesn't completely.
Yeah, and that's one of the big things I want to understand. Apparently, Einstein was disappointed that after he got general relativity, it didn't really fulfill Mach's principle, and I would like to understand it well enough to understand, quantitatively where does it go? What happens? Where does it go wrong?
Yeah, but I think there is a frame of reference in Mach's principle. Like there is a very special frame of reference, I think. Because when you rotate, I think he's saying that the stars at a distance, like if there are no stars, then you won't have this centrifugal force.
Right.
So,
yeah. So the.
But Einstein principle takes into account in one way that the metric tensor is dependent on all the mass in the universe. So one of the thing is local physical laws are determined by large-scale structure of the universe. So he's saying that his metric tensor of the universe will depend on everything that is in the universe. So which defines the laws of motion. Yeah, but it completely doesn't satisfy Mach's principle. It like vaguely satisfies Mach's principle.
Yeah. So I think.
But we'll have to read more about it.
When we understand enough, I think we'll know.
Yeah, we have to read Mach's principle more for it.
Yeah.
And the other thing is principle of least action, which I found very useful. Like I was looking at string theory as well and everything, quantum mechanics, quantum field theory. Everyone uses this principle of least action. So it's called the principle of stationary action, also variational principle that when applied to the action of mechanical system can be used to obtain the equation of motion for that system. So they say that the principle can be used to derive Newton and all, that's fine. Action must be minimized or maximized according to that. So if do you know Lagrangian and Hamiltonian?
I have seen that.
So Newtonian mechanics they can derive using principle of least action.
Yeah.
And even in the relativity they use action, then they minimize it. Even in string theory I saw they use action. They use this. According to them it's a very basic principle. I don't know why it exists. They don't know. But if you use that, you can derive Newtonian mechanics.
It seems that the advantage is you can use this in all different kinds of fields and always come up with a Lagrangian that works.
Yeah.
Susskind, if you look at the classical ones, he does a pretty good job on those, and he shows kind of in detail how to get how to replace Newton's laws with the Lagrangian and then with the Hamiltonian.
Yeah. I saw that they use it a lot.
Yeah.
So I need to look into it more as well. Then part 3 is relativity. So and special relativity. So I think what I need to read more is this Lagrangian and Hamiltonian principles and Mach's principle. It's I didn't understand it completely. I didn't read about it too much, but I need to read more.
I think I know how to derive. I have stood up there at one point, some time back, and derived the Lagrangian and stuff. while people were watching. I don't know if I can remember now, but
I
it's,
think the action is T minus P, right? Kinetic minus potential.
yeah. I mean, the trick is to there's some tricky little bits of calculus in there to make everything come out. But it's pretty cool, really. I'm curious if I could still do it. We'll have to.
I think doing it should be fine. I think it's just the integral which you have to minimize.
Yeah.
So they give the action you have to define.
Yeah. But you only do it once. I mean, it's really already done. Then you have those Euler's equations or something.
Yeah.
I forget what you call them. So they're already there. You don't really have to unless you want. But it's nice to understand where it came from.
Yeah. Then in special relativity, there was Galilean transformation in which t prime equal to t, then x prime equal to x minus vt. And if you are just traveling in x direction, and these were the simple laws, Galilean transformation. Then special relativity, there are only two postulates. The first is laws of physics are same in any inertial frame of reference, and the constancy of speed of light. Speed of light in vacuum is c in all inertial frames of reference. So these are the only two postulates. And using this, so they use x nu equal to ctx. So these are the, if you don't consider c as one, these are the coordinates t, x, y, z, ct, because this will have the length coordinate if you use ct. And if you draw those Minkowski diagrams, this is the light at 45 degree, v equal to c. This is x, ct. And these lines which the slope is more than 45 degrees is v is greater than c, which are not real line. We haven't seen such things in universe, at least till now. And this is v less than c, because it is a simple slope and all. I guess you know this.
Yeah.
Then in the relativity of simultaneity. So two events occur at the same. So if two events occur at the same place at the same time, like same place, same time, then all observers in the universe will agree that it occurs simultaneously. If it's same place, same time.
Yeah.
If it's different place and all, then it's different. And then there's a, I think this is the invariance of the interval, like del s square is c square del t square minus del x square.
Deltas. Those should be deltas.
Let me just write it here. The higher I go, my handwriting is going bad. Square is c square delta t square. So observers will agree on the space-time separation between any of the two events, where the separation of the interval is this. So everyone will agree on this. I think this is also called del tau square, the proper time. So this is the invariance of the interval. So when del s square is greater than 0, they are time-like intervals. When del s square is less than 0, it's space-like. And when it's equal to 0, it's light. So when it's equal to 0, that means this is equal to ct square, so it's light. And when it's greater than 0, it's time-like, which are the real intervals when it's greater than 0. When it's less than 0, it's space-like, and they are like when something is greater than speed of light. I guess you know the Lorentz transformation, right? Gamma equal to 1 upon root 1 minus b by c the whole square. This is the Lorentz, and the formulas are t prime into gamma t minus bx by c square, and x prime equal to gamma x minus vt, and the motion is just in x direction, y prime equal to y and z prime equal to z. So these are those transformations, and there is a very simple derivation. Do you know the derivation of this?
Yeah, I've seen it.
Yeah, so it's a very. I'll just give a gist. So you can say that t prime, which is the prime frame of reference, equal to a0 plus a1t plus a2x plus a3t square, and so on, like Taylor series or whatever it's called. And same for x prime, equal to b0 plus b1t b1x plus b2t plus b3x square plus b4t square plus b2. So then they neglect the higher order terms because of the linear relationship of you assume there is a linear relationship and omit the higher, because they are saying Newton's first law holds in all inertial frames, meaning frames cannot be accelerating, and therefore we assume a linear relationship since there is no acceleration. And then if you neglect all these terms, then you get like this. Then you can say that they are both coinciding at origin at when t prime t equal to 0, so these both will be 0. So t prime will be a1t plus a2x, and x prime will be b1x plus b2t. And then using a very you should use that velocity of c is constant. Using that, if you manipulate, do you want me to go through it or no? Right? So manipulating it, you will get those, like using very basic algebra, you will get the transformation laws. So it's very simple. It just there's a postulate that velocity of light is constant.
Yeah.
Using this and then saying that c is constant, you can very easily come up with those transformation laws. Then you know how they write the Lorentz transformation matrix, right? I'll just write it down. So I'll just write down what gamma is here. Gamma is 1 upon root 1 minus b by c the whole square. B is the relative velocity between the two frames of reference. So Lorentz transformation is ct prime x prime y prime z prime gamma minus gamma b by c 0 0 minus gamma b by c gamma 0 0 0 0 0 0 0 c x y z. So this is how the two transform. So proper time and time dilation. So proper time is actually the ct square minus x square y square. So for any two frames, so coordinate time is that this t, and proper time is tau. They write it as tau. So you know time dilation and everything, right?
Yeah.
Time dilation is fine. So basically proper time tau is coordinate time difference divided by gamma. Proper time. So another way of saying is that the process that takes a certain proper time, measured by the definition in its own rest frame, like the particle which is moving at speed v, he measures its own time as proper time, has a longer duration measured by another observer moving relative to the rest frame. That is, if something is if someone else is measuring and he is moving, then he will measure that he is taking longer time.
Yeah.
Then length contraction, you can have a similar derivation, and So length contraction is L is LP by gamma.
Oh, the,
Like L.
okay, LP is the proper.
Yeah.
Okay.
So it goes runs
Yeah,
on.
yeah.
And then there's an end of simultaneity. So two events occur simultaneously in S frame. Like why is there an end of simultaneity according to the formulas? So according to formulas is gamma delta t minus v delta x by c square. This is the transformation. And if two events occur simultaneously in frame S, then delta t equal to 0. If in frame S they occur simultaneously in delta space, this is equal to 0. But delta t prime equal to gamma minus v delta x by c square. So they won't happen simultaneously. But if they occur at the same place, then this is equal to 0 and then it's simultaneous. And if you consider v is very very less than c, then it comes down to Galilean transformation. Invariance of time interval, you know that. Invariance of proper time, it's the same thing. So this applies for everything, that invariance of time c square delta tau square, which is proper time, is delta s square equal to c square delta t square, which we already wrote, delta x square minus delta y square minus delta z square. And it's for everything, not just they are saying the above tells us not only proper time between events occurring at same position, but is applied to time separated events measured from any frame. Like you can be space separated, time separated, and can measure this for any reference frame. Then the Minkowski metric. So I think for flat space, I think you know that, right? 1 0 0 0 and something, that's a Minkowski metric. And then spherical coordinates. Then there's a conservation of laws, like so there's conservation of energy and momentum in this. So one of the invariant physical quantity is rest mass, m. The rest mass won't change. The relationship between various invariant physical quantities can be described using equations. If these equations are invariant, they are called invariant or covariant. Like if those equations. That is, if these equations they take the same form in all inertial frames, they are invariant or covariant. And it's one of the postulates as well of relativity that the law should be.
Yeah.
Then they called this as the 4 velocity. To proper time.
Yeah.
For velocity. Which comes down to this gamma CV. You substitute proper time as coordinate time on gamma, like we are saying x0 will be ct equal to gamma c tau. So u0 will be dx 0 by d tau to c gamma. And other things come out to be, the three other spatial velocities come out to be gamma v. So this finally comes down to this. And one of the invariant quantities is Minkowski metric c square. So multiply those two four velocities.
Yeah, now this was an interesting formula because in a sense this is the, this is the length of every velocity vector,
Length of every, yeah.
the norm, if you will. So it, in a sense, it's kind of like,
Square of the,
it's kind of like everything travels at the speed of light in a sense. It can be divided up over space and time, but in a way, everything, in some sense, everything is going the same speed. You know what I'm saying?
yeah, this is the length, yeah.
Yeah.
So g nu of the velocity vector.
Yeah.
You're saying everything is traveling at the speed of light.
Yeah, in a sense, it's just a matter of whether it travels through time or through space.
Space time.
Yeah.
If you
But if you look at it in a way, it's travel in space time. It's always, in some sense, it's the same.
I haven't looked at it deeply, but yeah, you're right. You can look at it, what it exactly means and what are the
Yeah.
implications.
Yeah.
Then there is relativistic momentum, which eventually comes down to m gamma v.
Now this one, okay, so the zero component,
No, I mean, this is just a spatial component right now.
oh, you're just, okay, we haven't got to
Yeah.
capital P, I guess you call it.
This is just p, x, y, z. This comes to p gamma v. Because this is only because we had the four velocities with respect to proper time.
Yeah.
Then they derive the relativistic kinetic energy, which comes down to gamma minus 1 mc square. Kinetic energy, relativistic. So, I mean, that book has basic, it's very trivial derivative, not trivial, but you have integration and all, but it's basic, like, tell you what they're doing is work is f dx, and for f they put ma, and for acceleration they put d by dt, dv by dt. Then they have the chain rule, dv by dt is dv by dx, dx by dt, and dx by dt is v. So they have mv dv, then they integrate it, and then m is also function of velocity because of m upon 1 minus v square. Integrate it, and then they get this eventually. And if you see, even in this, I think, even in that equation, if you see if v is very less than c, then kinetic energy will come down to half mv square.
Uh-huh.
Because this gamma is 1 upon root 1 minus v square by c square.
Yeah.
V is really very less, and if you expand that Taylor series, or if you apply this series,
Yeah, I remember, I saw that, yeah.
so total relativistic energy is this total relativistic is gamma mc square, which is equal to kinetic energy relativistic plus mc square. So like this, mc square is gamma mc square. So the zero, that E zero equal to mc square, that velocity is 0. When this is 0, you have mc square. When velocity is 0, 1 upon v square, this will be 0. because this gamma is 1 upon the root 1 minus c square by c square, so this will become 1.
Mhm.
So you will have just mc square, which is at equal to mc square only when you are at rest. So now if you look at the 4 momentum again, this is 4 velocity is gamma cv that we already saw, equal to c gamma v gamma. So p momentum is mc gamma m gamma v. Now E equal to gamma mc square and P equal to m gamma v. So this is equal to E by C. If you bring one C here, so P nu equal to E by C equal to E by C px P by to add something.
So this E, so I was a little bit confused on one point about this. So the E here in the zero component is the E of,
It's a total energy of the particle. Like if it's moving at a velocity v,
so it
it's gamma
includes,
mc square basically. It's a kinetic and m0 mc square rest mass c square plus kinetic energy that we saw earlier.
so it really is the total energy. I
Yeah.
knew we called it that.
So total energy is generally gamma mc square. So E is actually equal to gamma mc square, not mc square. So when it's at rest, gamma is 1 by 1 upon root 2. What is it? So when it's 0, this is 1.
Yeah, I'm with you. So that really is the total energy,
Yeah.
not just the kinetic, okay.
That's it. So 4 momentum provides a complete description of total relativistic energy, its time component and relativistic momentum spatial components. 4 momentum of a particle is a vector where the components in some frame give the particle energy and momentum related to that frame. As we will see later, all important energy momentum tensor, the right hand. So it basically comes at the right hand side of the field equations. But the thing to take out is that mass